Hello all. This video is about logarithms. This is kind of a big one. Logarithms are a little out there. They're a little different. They're what are called transcendental functions. So both exponential and logarithmic functions are referred to as transcendental, if you hear someone mention that. Algebraic functions are polynomials or rational functions. We've already talked about all of those. An exponential function is of this form here, and its inverse function is here. So a logarithmic function and an exponential function are exactly inverses of one another. Both exponential and logarithmic functions are one-to-one, so they are, once again, inverses of one another. And you can see the domain and range switch between the two of them. It's important that we are able to switch from exponential form into logarithmic form. So here's exponential form, and you can exactly see the 2 here becomes the base of the logarithm. The part that's by itself becomes the domain of the logarithm, and the exponent is all by itself now. And you can see a similar pattern here. So it's log base 5 of 25 equals 2. And you can see a few more examples here. So common and natural logs, these are the most common. So here we have what's called a natural log. This means that it's base e. I know that's real small and hard to see, but that's that same e that we talked about in a previous video. This is log base 10 of x. We don't write the 10 in. This is called the common log. The common log is used for things like the Richter scale, things for like pH levels in chemistry. Those are all common logarithms. The natural log is one of those, that e, again, is one of those things that comes up in nature all over the place. We use it a lot in calculus. So if we have a logarithmic function and its inverse, that exponential function, when we composite the two, they cancel. So when we put the two together, they completely undo one another. Once again, you can see on a calculator, log and its inverse 10 to the x, natural log and its inverse e to the x. So it's all kind of out there. Here you can see these two are going to cancel one another out because this is putting an exponential inside of a logarithmic of the same base, and so we just get x. Natural log is base e. We don't write the e in. We just know that ln means natural log to the 7th, and we just get a 7. And here, log base 10 is the common log of 10. That exponent is a 1, so we get 9 times 1, which is just 9. Here we're going in the other direction. Here we have 3 raised to the log base 3, so again, they're inverses, they cancel. Here, natural log is base e, so again, they cancel. And here, you can see they cancel as well. So graphing logarithmic functions, we're not going to spend a lot of time with this, but you can see here's my exponential function, my y equals 2 to the x, and its exact mirror image across y equals x is here. You can see this exponential function is asymptotic over the x-axis, or y equals 0. All that switches for the logarithmic, it's asymptotic on the y-axis, or when x equals 0. And again, you can see it's a mirror reflection across the line y equals x. I'm going to skip this one. That one's a little complicated. And here we have a generic logarithmic function. Now, when b is bigger than 1, it looks like this. And when b is between 0 and 1, it kind of has an opposite effect. So now we're going to talk domain. We can only take the log of a positive value. I'd like to show you in the calculator that if I take the common log of 10, I should get 1. But if I take the log of negative 10, it's not going to like that. So it doesn't like that. We can't take the log of negative numbers. We can using complex numbers in higher mathematics, but that's way outside the scope of this course. So we're just going to say whatever the domain there is, it's got to be positive. So what's the domain of this? Well, x minus 7. You can see when x equals 0, we have a problem. We get log base b of negative 7, and as I just showed, you can't do that. So what we're going to do is we're going to take the domain and set it bigger than 0. Notice it's strictly bigger than 0. It's not equal to 0. We can't take the log of 0. I'll demonstrate that as well. So log of 0, again, we have a problem.
So
what we do is we take the domain, set it bigger than 0, and then solve for x. So what's our domain? It's got to be only values that are bigger than 7. So 7.1, no problem. 7 itself, no good, so we don't include it. So we put the parenthesis. So we're going to continue finding the domain. That's going to be setting the inside bigger than 0 and solving for x. Here, we have a quadratic inside, bigger than 0, so what we have to do is factor it, and then use the idea of a parabola. So it's positive up here, positive over here, and negative down here, and we only want where it's positive. So that's negative infinity to negative 2, and then from 2 on. The domain here, once again, let's select the one above it, bigger than 0, so 1/2 to infinity. This one's a little more complicated. Here we have a rational inside here. So to make that positive, what I'm going to have to do is I'm going to have to go through and test the numerator and denominator. So numbers that, besides -1 and +2, those are my breaking points. And for sure, x can't be 2 ever, even if it was an equal there, which it isn't. But if it was, we would not include that there. And once again, we can see when we test numbers in the various regions, we can see the positive is from negative infinity to -1. And then this is the union or 2 and on is going to be our domain in that case in interval notation. I'm going to skip this next part. So I'm going to solve this equation. Now I'm going to notice that this is the natural log, which is base e of e. And if you remember, they cancel out completely. So I just end up with 2x equals 10, or x equals 5. This one, once again, we're going to convert kind of like we did here. We're going to go from logarithmic form into exponential form. And you can see that means that the x minus 2 is going to be by itself, and then I'm going to get 4 raised to the second power. So that's where that comes from. And then solve for x.